Hello and welcome to the 18th lecture of this short course called Behavioral Theory of Systems with a view towards data driven control. Now we were at the juncture of a very important concept, namely controllability of behaviors. So we introduced the problem, we did not introduce the problem though, we sort of got a glimpse of the problem when we are trying to do this elimination, and we found out that eliminating state variables from a state representation of a system whose transfer function was known to us, but with the same transfer function we obtained two distinct behaviors. The two behaviors are guaranteed to be unequal because their row modules are different, because their row modules are unequal. In fact, this row module was smaller, was contained in this row module. So therefore this behavior contains this behavior, and I kind of hinted at the fact that this is so because this is an uncontrollable behavior, and this was the so called controllable part of this behavior, although I did not mention this term at the time, but we will see this. And with this I also alluded to the fact that this means that behavior, controllability is a property of the behavior, not a property of its representation, be it state or otherwise, right. So how do we define this controllability of a behavior, independent of its representation? So this definition is by Yancey Willems. This is the crowning achievement of behavioral theory. Willems was the forefather, the originator of behavioral theory, and this was Willems's definition of behavioral theory of behavioral controllability, and we will see that in fact this idea of controllability generalizes the idea of controllability as per Kalman, okay. But that will come later. Right now we are going to concentrate on the idea of controllability of a behavior. What do we mean by controllability of a behavior? Now once again let us assume we have a behavior B. We assume that it is a linear shift invariant behavior, So LTI systems behavior given by differential equations is what we will see next, but we do not have to assume that it's it's given by differential equations, but we do not worry about that as of now, So we assume that it is a linear differential behavior given by a system of ordinary differential equations with constant coefficients, okay. Now we also assume that it is a C infinity behavior, okay. So the trajectories are C infinity. Now when do we call such a behavior controllable? Let me first give you its trajectory level definition, and then I will give you the give you a sort of picture, an illustration of what it really means, okay. So this will be called controllable if, so B is defined to be controllable if the following happens: for every pair of W1 W2 in the behavior, and for every tau strictly bigger than 0, there exists a W in the behavior such that Wt is equal to W1t for all t less than or equal to 0, and it is equal to W2t for all t bigger than or equal to tau. That is the definition of controllability. Let me reiterate. For every pair of trajectories in the behavior, there exists and a time interval tau, there exists another trajectory in the same behavior which matches with trajectory W1 in the past, trajectory W2 in the future, starting after some time, after the given interval tau. But this tau can be arbitrarily small, as you can see that this I say for all tau. So this tau can be arbitrarily small, as long as it is bigger than 0, as long as it is non-zero, it is enough, right. pictorially what does this mean? So, let me just draw this picture. Yeah, it is very difficult to draw something that is inherently more than dimension 3 on a 2D piece of paper. I will try my best. So, okay, this is my time axis and this is my signal space. Okay, let me use the same color, or let me use black color to draw 2 snapshots of the signal space at 2 times. Yeah, this is some time and this is another snapshot of the same signal space at another time. So, for us this is tau, this is 0. You see the definition, if I do not assume shift invariance, then the definition will have some t naught here and t naught plus tau here, where the t naught is some number on the timeline, but because I have assumed time invariance, that t naught can be brought to 0 without loss of generality. Okay. Now, given 2 trajectories, okay, let me use a this color. Yeah. So, this is a trajectory, an arbitrary trajectory. This is an arbitrary trajectory, we call it W1. Then I use another arbitrary trajectory, this is another arbitrary trajectory, we call it W2. 2 arbitrary trajectories. Controllability would mean that for these arbitrary trajectories there is also another trajectory, green one, which matches W1 before t equal to 0 and matches W2 after t is tau. In between, well, in between we should be able to get a patch between the two, so that the entire green trajectory, that is W, is a C infinity trajectory within the behavior. That is the pictorial representation of controllability. Yeah, I hope you understand the things that are that are for which I have used for all. Yeah, these are just 2 representations of 2 arbitrary trajectories. This should be, we should be able to do this patching for arbitrary pairs of trajectories, and also this duration, this time duration from 0 to tau, that should also be arbitrary. Okay, but there should be a finite gap between the 2. It cannot be 0. I cannot instantaneously go from one trajectory to another trajectory. That is outrageous, because in that case there could be jumps, and jumps are not allowed for C infinity trajectories. So, this tau is required to have this patching done in a C infinity manner, right. So, is that okay? This is the idea of controllability, Williams's idea of controllability of a behavior. Go back to the definition. Yeah, look at the definition and then look at the picture. So, keep this in mind as we move along and discuss the ideas related to this idea of controllability. Now, so far so good, no problem. There is a okay, interesting enough definition of controllability, but what does this really mean? Yeah, the idea of controllability then can be, loosely speaking, given an equivalent name, namely patchability of trajectories. That the trajectories, arbitrary pairs of trajectories, can be patched in a C infinity manner. Well, let us look at some examples of such patching. Yeah, like for example, suppose my behavior is just C infinity, all of C infinity. C infinity R to R. I am looking at all trajectories. Is this controllable? Yeah, is this controllable? Well, of course it is, because you see it is already known. So, this will go to you as an exercise. Show explicitly that if you have two C infinity trajectories, arbitrary C infinity trajectories, you can fix this t equal to 0 and any arbitrary time tau, it is possible to go from one C infinity trajectory to another C infinity trajectory without ever losing your C infinity-ness, yeah, without losing the smoothness. Yeah, okay. In fact, this is possible to do because you see, if you have 0 and somebody gives you some other number, yeah, then from 0 to that number there exists a function which is C infinity and it is 0 behind this line and it is this value beyond this line. In between this patch is C infinity. That is the reason why C infinity trajectories are patchable with each other. Yeah, this goes to you as an exercise to find out this patch. What should this patch be? Yeah, there are standard answers to this question, so that is why I am giving it to you as an exercise. You can do a fun googling around to find out an answer for this question. Okay, let us see infinity is patchable. What about this behavior? Suppose I look at this behavior, dw dt is equal to 0. This is my behavior. What are the solutions? dw dt equal to 0, wt must be equal to a constant. Is this behavior controllable? What do you think? Is it patchable? Let us say we take two trajectories. What will it should we take? Take k to be equal to 1. Yeah, so that is one trajectory. So w, let me call it w1, fine. w1 is equal to 1 for all t, yeah, sorry, for all t. And what is w2? Let us say w2 I take 0 for all t. Yeah. So I have, so let me draw the picture again. Where should I draw the picture? Yeah, here. The picture t. This is t equal to 0. This is t equal to some tau. Somebody has given me a tau. I want a trajectory which is 1 up to this point and it is 0 beyond tau, and I patch it like this, so that this entire new patched thing must also satisfy dw dt equal to 0. Is it possible? You tell me. Of course not, because any solution of dw dt must be 0, must be constant all along. This is not a constant, this is not a constant, this was constant and then it became another constant, but in between why should it satisfy this dw dt equal to 0? It does not. And this k was arbitrary, yeah, no, whatever k you, instead of 0 if you want to take k1 and k2, then also same question arises. I want to have something which is k1 for some time and then beyond some time it should be k2, in between I should be able to patch them so that I still have a solution to this differential equation. That's outrageous, that is not possible, because solution of this differential equation must always be constant. Yeah, if this is like too simple for you, just convince yourself about the fact that dw dt plus some lambda times w, this differential equation equal to 0. If I want solutions for this, whose solutions I know is e to the power minus lambda t times a constant, these solutions also are not patchable. The reason being, how does it look? It looks like this, no, every solution. And suppose I want to patch it with, let's say 0 trajectory. Suppose 0 trajectory I want to patch it with. So this is t equal to 0. So I want my solution to be 0 for t bigger than for t less than t equal to 0. for t less than 0, less than or equal to 0, and beyond some time I want this to be follow this trajectory. So, in between I should be able to patch it C infinity in a C infinity manner. Is it possible? Well, it is not, because why? Because for such an equation, this solution that I am getting, this solution gets fixed by this k all along for all time. If beyond tau the solution has to follow this trajectory, then before tau it has to follow this trajectory only, otherwise it is not a solution. Yeah, because you know, for this thing, if somebody gives me a w and says that w belongs to the kernel of d dt plus lambda. Yeah, if this is so, then I will just look at w and I will find out w, what is the value of w at some particular point, let us say capital T, and this value, let me call it some k tilde, this value uniquely determines the trajectory, uniquely determines w. Yeah, indeed. How do you get that? So, I know that the trajectory must be of the form this, and at t equal to capital T, this is equal to k tilde. So, from here I will be able to find out what is k, namely k must be equal to k tilde given value divided by e to the power minus lambda given capital time. So, this k is the one that gives us the trajectory completely. So, therefore, if the patched version also is a trajectory, then that patched version must also have this form only, and a patched version can never have this form, because this form gets immediately fixed by its value at some time. Okay, that is the problem. In fact, with a stretch you can actually show that as long as your R xi matrix is a square q cross q matrix with determinant not equal to 0, kernel of R xi cannot be autonomous, cannot be controllable, because such cases are, as if you remember, the so called autonomous systems. Autonomous systems are the stark opposite to controllable systems. Yeah. So, such autonomous systems are never controllable. So, we have an example of a system which is not controllable. Okay. Can we have then, so when do we have controllability then? Yeah. Well, I will give you one example of controllability, and then we will see that, going a little further ahead of ourselves, we will see that controllable systems are in fact characterized by such descriptions. Namely, suppose you have a behavior which is given by a latent variable representation w, such that there exists an L in C infinity R to R m with the property that w is equal to m xi acting on L. Yeah. In this case, you see the way we have defined it, this is in fact the image of the operator matrix m xi. I say such a system is controllable, guaranteed to be controllable. Why so? Because of the following. You see, somebody gives me a w1, then w1 must be equal to some m xi L1, and somebody gives me a w2 m xi L2, and I want to patch w1 and w2, right, to get a w, so which is also in the behavior. Just patch L1 and L2, no? Yeah. So, take L which is equal to L1. So, LT is equal to L1T for all t less than or equal to 0, and is equal to L2T for all t bigger than or equal to tau. Then take this L. Obviously, if I define WT, if I define W to be equal to m xi acting on this L, then obviously this implies W will satisfy is equal to m xi L t for all t less than or equal to 0, which is equal to m xi L1 t for all t less than or equal to 0, which is equal to W1 t for all t less than or equal to 0. And likewise with same calculations you can show that this will be equal to W2 t for all t bigger than or equal to tau. So, patching is done. The only question remains is that is this L also C infinity? Well, it is, as we have already checked via your exercise problem, that all of C infinity is patchable. L here is coming from arbitrary C infinity functions. Yeah, this L is an arbitrary C infinity function. So, of course, if somebody gives me one C infinity function N1 and then another C infinity function L2, I can always patch them to get my L, which is also a C infinity function, and with that L I have patchability. Pictorially, if this is your behavior given by an image, means that it is the image of this all of C infinity functions that gets mapped to the behavior B, and because I have arbitrary patchability here, because it is an image, this arbitrary patchability gets transferred. Yeah, so that is why image representation is controllable. Okay. Now that we have seen examples of both controllable and uncontrollable, yeah, and autonomous in fact, obviously we know that it immediately follows that not every system is controllable, neither is every system autonomous. Yeah, the fact that every system is not autonomous is easily seen, because for autonomy you need square matrices with non-zero determinant, and of course there are so many counter representation matrices which are not square, or even if they are square their determinant is not non-zero. Yeah. So, in that situation it brings us to this question that there are systems which are neither controllable nor autonomous. So, of course, they will be uncontrollable. How do we characterize such systems? That also tells us that not every system has an image representation. Yeah, because if it had an image representation it would be controllable. It will turn out, as we will see very soon, that it is in fact controllability can in fact be characterized by having an image representation. A system is controllable if and only if it has an image representation, it admits an image representation. This very simple exercise that we did here, that shows that sufficiency of image representation for controllability. It does not show necessity, but it also is necessary, is what we are going to see next. Yeah, it is what we are going to see now. So, how do we characterize this idea of controllability? I mean, let us just face it that given this definition of controllability, it is immensely difficult to implement that definition to get to get a check of controllability. How do you check whether something is controllable or not? If you have to check for all possible pairs and their patchability, it is like an impossible task. It is never possible to do it. So, the question is, in that case, is there an easier check? And I mean, hopefully would there be an algebraic test like for Kalman controllability test, given this A B matrices, you just look at B, A B, A square B and find out the rank. That is an algebraic test. Is it possible to have a similar algebraic kind of a test for controllability of behaviors as well? To do that, what we will do is we will do this, we will do this chain of arguments. Some theoretical results will derive, which will give us conditions for controllability, and we will complete this chain so as to ensure that all of these conditions, each one of them is a necessary and sufficient condition for controllability. Okay. So, the first link in this chain of arguments is as follows. I have not defined this term. We will come back to this page again and again. So, that is why I am going to skip to the next page where I do this, I prove this argument. First I define what is what is an FLP kernel representation matrix? FLP is the short form for factor left prime. Yeah, in short FLP. What is factor left prime? Given a polynomial matrix, yeah, of size R G cross Q, we first assume that it is full row rank. We have seen that we can do this assumption, we can make this assumption without loss of generality. So, we have a full row rank polynomial matrix R psi. When is it called factor left prime? Suppose I factorize R psi as a factor f psi and R 0 psi, where the sizes needs to be specified. This is a matrix of size G cross Q like R psi itself, and this is a square G cross G matrix. R psi is called factor left prime, if by definition, so that is why I do not have to say if and only if for all such factorizations R psi equal to f psi times R 0 psi, f psi is necessarily unimodular. That means, whenever you factorize the polynomial matrix into f times r, a square matrix times this matrix of the same size, f must be unimodular. You cannot have a non-unimodular square factor pulled out of the matrix, then it is called factor left prime. Let me give you a quick and simple example, so that you get the idea clearly. What is this example? Well, you see, look at two polynomials P psi and Q psi, right. Very simple situation. When can you say this is factor left prime? When can you pull out a factor? If and only if they have common factors, isn't it? Otherwise, how will you pull out a factor? You can pull out only a constant factor, yeah, which is unimodular in this case. Unimodular matrix of size 1 by 1 must be non-zero constants. So, therefore, this is FLP if and only if P and Q are co-prime, that is their GCD is equal to 1, yeah, that is factor left prime. But of course, if you have a bigger matrix, then factor left prime means you need bigger checks for doing factor left prime. Like, for example, suppose you have something like xi plus 1 and xi plus 2 and xi plus 3 and xi plus 4 and let us say 0 0, yeah, is this factor left prime? Well, we have to check. Let me make it a little easier for you. Let us say this is, now it will be easier, 0 0. Is this factor left prime? This is not factor left prime, because immediately you can see that you can write this guy down as xi plus 1 0 0 xi plus 4 multiplying 1 0 0 1 0 0. Yeah, this is a factorization and this is not unimodular, you see. So, to get your ideas, to get your ideas sort of to get a handle on what is going on here, think of them as scalar matrix, this situation, think of them as like this, okay, P Q, and being factor left prime means there are no common factors between these two polynomials. Yeah? That should be your base case of understanding, so that you can understand what is going on later on. So, this link of the chain of arguments that we are going to prove, first one says that controllability implies that it is a factor left prime matrix, kernel representation matrix. Kernel representations can always be assumed to be full row rank, as we have seen before, by doing row operations, unimodular row operations. You can bring them to upper triangular form and so on, which means that they are assumed to be assumed to be full row rank without loss of generality. What I am saying here is that controllability should imply factorial f prime, which means if I have a full row rank kernel representation which is not factorial f prime, then the corresponding behavior B given by kernel of R xi will also be not controllable, should be uncontrollable. Why is that so? In fact, very simple arguments will prove that if it is not factorial f prime, it cannot be controllable, and we will show that if it is not factorial f prime, then we can actually construct trajectories within the system which are not patchable, right. That is the first chain of the first link in the chain. This will be followed by several others which will once again circle back to controllability, which will give us necessary and sufficient conditions for controllability. Okay. All right. So, given an R xi which is not factorial f prime, I should be able to factorize this as f xi and R 0 xi, right. Now, let us take a W which is in the kernel of R xi, right. So, that means R xi acting on W produces 0, but I also assume that W when gets acted upon by R naught xi, that is not equal to 0. Obviously, I can find such things because otherwise these two row modules will be the same. No, if everything that is in the kernel of R xi is also in the kernel of R naught xi, right. So, that would mean the module R. So I must then have this behavior contained in this behavior. So, I must then have this, right. Every behavior. So, if kernel of R xi is contained in kernel of R naught xi, then this is a bigger behavior. So, it should be a smaller module, right. It should be a smaller module, right. So, we must have something like this, right. But because of this structure, every row of R is in the row span of R naught. So, R naught anyway contains R from this factorization, which means R must then be equal to R naught, which means the two behaviors must be equal, but that is obviously not true, because you see this is a non-unimodular matrix. For it to be not factorial f prime, it has to be a non-unimodular matrix. So, if two matrices are related by non-unimodular matrices, then the modules cannot be equal to each other, right. So, in fact, we have this strict inequality. This is not the case. So, therefore, I will always be able to find out a W which is in the kernel of R, but not in the kernel of R naught. This non-zero trajectory is what I define as V. Okay. But because W R xi is equal to 0, this implies V must be in the kernel of f xi, and this is a non-unimodular matrix, square matrix. So, it means that it has a non-zero determinant, and the determinant is a non-constant polynomial. Yeah. So, therefore, this is an autonomous system. Right. Now, here is the contradiction. If W were to be patchable, if W were patchable with the 0 trajectory, then V patched with 0 trajectory must be in the kernel of f xi but that is absurd, because it is an autonomous system. Autonomous system trajectories are not patchable with the 0 trajectory. So, that is a contradiction, which means it is not controllable. So, not FLP implies not controllable, which means we have our first chain proved. The next chain and many more is what we are going to see in the next lectures. Okay. So, please bear with us till then. Take care. Bye from my side.